Hey there, it's me again, Sam. Today I'm going to talk about intermolecular forces. So, when two atoms and molecules, what are the types of forces that can bring them together? And I'm also going to talk about how that can affect the boiling point. Here we go. Okay, first of all, let's define what intermolecular forces are. The intermolecular forces are the electrostatic forces between molecules or atoms. I'll just write molecules. Okay, so let's plunge right into it. Whoa, sorry about that. Anyways, what are the types of electrostatic forces? In fact, I'll do it right underneath. Whoa, this is pretty thick. Okay. What are the types? Yeah, that's better. Types. Now there are lots of types and I'm gonna have to explain each one. Okay. Let's start with ion-ion bonds. Now, this is the first bond, and it's actually, this bond is the strongest bond due to, I'll just underline this, due to its formal force. I'll explain that in a sec. So, example, what? It's salt. Is literally an example. Table salt. Sodium chloride. Oops. NaCl. That's literally an example. Because that's an ionic bond. Yeah. I made a video on how to tell ionic bonds, how to balance them, and pick any random two, but this is the balanced form. Yeah, NaCl. Anyways, so this is what I'm talking about. Let me explain. Actually, there isn't much to explain for this one. NaCl is just, when you do an ionic bond, it's because, let's say here's Na and here's Cl. So let's say, well, since this one is the metal, it gives the electron. So this one gives this one an electron. Now, since electrons are a negative charge, this one just lost, Na just lost one electron, so it's now positive, because it lost a negative, so it's now more positive. Now, chlorine just gained an electron, so it's now more negative. Now, just like in magnets, positive and negative attract. So this is literally, it's really strong, like a magnet. I made a video on magnets, 10 years ago. Anyways, going on to the next one. It will be ion dipole. I'll kind of go down a little bit. Ion dipole forces. Well, to understand this, you need to understand what a dipole is. Well, a dipole is kind of polarity. Not clarity, polarity. I'll make a video on that soon. Maybe a few videos later. So polarity is, let's say, let me draw a water molecule. There's two hydrogens, but they both have only one electron, so they're not that strong, you could say. Their quote-unquote gravitational force is not that good. And then here it is, the much more massive oxygen. Yeah, that's an O. Let me write that better. So, because oxygen is more electronegative. I'll explain that in the next video. So this is actually a polar molecule. Oops. Whoa. Polar molecule. So this means that electrons spent a little bit more time near the oxygen. Even though they're still going like this, they still spend a little bit more time near the oxygen. So there's a little bit negative charge this way, and a little bit negative charge this way, and a little positive one. So you can see that there is an overall negative charge this way. Now, if we know that, we now know that the top side, for now, of oxygen is actually more negative than the bottom. Redrawing this: oxygen, hydrogen, hydrogen. So now if sodium chloride comes, sodium, NaCl. When sodium chloride comes, I told you sodium is positive and chloride is negative. And since I just told you oxygen is negative and the hydrogens are positive, sodium, which is positive, will get attracted to oxygen, which is negative. And the chloride, which is negative, will get attracted to the hydrogens, which are positive. That's why salt dissolves in water, because it's polar. Not polar bear. Rawr. Anyways, next one, dipole-dipole attraction. Dipole-dipole. So this is when water itself, water is the dipole because it has that attraction, oxygen and hydrogen. That was a dipole. Well, that's when it itself lines up. So kind of what has happened? Anyways, so if this is oxygen, hydrogen, hydrogen. Oopsie. So, and now let's say there's another one over here, another water molecule. So you can see that the hydrogens, I told you, are more positive, the oxygen more negative. This one too, the oxygen is negative, this is positive. So now positive wants to go to negative, and negative, and this positive wants to go to this negative too. So they arrange themselves in such a way: oxygen, hydrogen, hydrogen. So, and then the other oxygen comes over here: oxygen, hydrogen, hydrogen. And then there's a third one: oxygen, hydrogen, and hydrogen. So they kind of, water arranges itself into a fluid crystal, kind of. So this was dipole-dipole when they arranged themselves in this one. Now the next one is, well, let's say now we do this strange one. It's kind of the strangest. It has two names: Van der Waals, and it's also known as an easier London dispersion. Don't ask me why it's named that. So technically what it is let's take helium. In my video about how to name these chemical compounds, I told you in the innermost shell you just need two to be stable, and helium does have two. There's one over here and one over here. So it is technically stable, so it doesn't bond with anything. But occasionally, the helium leans a little bit just over here. So the nucleus is a little bit to this side. That means because the nucleus is positive, it contains protons, which are positive, and neutrons, which have no charge at all. The net force is positive because neutrons don't do anything. So now the positive has moved more to this side and it's moved away from this side. So this is going to be more negative and this is going to be more positive. Just a very slight force. But what happens is, if there's a partner helium over here, this positive coming near the positive will force this helium away. So now this side is positive and this is negative. These two come together. This is the very, very weak van der Waals or London dispersion force. These were these four forces. Now let me tell you about how these affect boiling point. Let's say I took all three of these. Let's say comparative forces. So I don't know which one to pick. Okay, sodium chloride, NaCl, and someone else. Who else? Let's just take H2O. Yeah, I won't compare the ion dipole. I'll just compare these three. And then the one, I'll just take helium again. Now, NaCl. Now, let's say it's 0 Kelvin, which is negative 273 degrees Celsius. Yes, it's cold. And I told you in my video about the zeroth law of thermodynamics that it's actually impossible to ever reach 0 Kelvin. But let's just say somehow we reach this. Now, in this case, all of them, even helium, is a solid. Yes, helium is a gas, but it too is a solid at 0 Kelvin. Now, let's say we slowly start increasing the temperature. And I want to tell you that the higher the heat, the higher the force there is trying to pull these apart. Now, I told you that, well, let me mark these actually. Ion, dipole, and this one was the London Gatwick Airport or something. London dispersion. Okay. Now let's say it's 0 Kelvin. No, wait, I'm gonna write Kelvin is 0 right now. Now let's say I make this 1 Kelvin. At 1 Kelvin, helium just turns straight into a liquid. Yes, it already turned at 1 Kelvin into a liquid. Why? Because it's the London, what was it called? London dispersion, yes. London dispersion force, I told you, is very, very weak. So, yeah, it's really weak. So, there's only 1 Kelvin needed to pull it apart, and it turns into a liquid. In fact, just less than 1 Kelvin. Now, we've done 1 Kelvin. Now, what happens? We keep increasing the temperature. 2 Kelvin, nothing happens. 3 Kelvin, nothing happens. We go up all the way to 273 Kelvin. That is when the dipole of hydrogen, H2O or water, finally breaks. It turns into a liquid. We keep increasing the temperature. 373 Kelvin. That's when this turns into a gas. Yeah, that's 100 degrees Celsius. Keep increasing. We're at what? Okay. We're increasing it. We're now at 1000 Kelvin, and this is still a solid. What is going on? Ion. This is salt, by the way, table salt. 1000, where it's still going, and then finally, at 1074 Kelvin, it turns into a liquid. See how powerful this is, NaCl, and how weak helium is? I'm kidding. Anyways, that was it for today's video. See you next time.